Good morning, Townview. So today we're going to be talking about nuclear energy. So top of your page, let's all write down nuclear energy or just nuclear. Let's go ahead and move on. But before we get into it, I got a question for you. When you hear nuclear, what do you think of? We don't use the B word in here. What else do you think about when you hear the word nuclear? What do you think nuclear means? All right, so I heard atoms, explosives, radioactive, sure. All right, so the definition I'm going to give you for nuclear is actually a very simple one. So our definition for nuclear is going to be anytime there's a change within the nucleus. Y'all remember the nucleus? What lives in the nucleus? Protons and neutrons. So anytime you have a nuclear change, there's also a change in electrons. However, electrons don't decide, they don't reside within the nucleus, so they don't determine a nuclear reaction. But anytime there's a change within the nucleus of an atom, we call that a nuclear reaction. So if you remove a proton, if you add a neutron, if you convert a neutron into a proton, if you convert a proton into a neutron, all of these are things that you can do, and all of them are considered nuclear reactions. Now, the next thing I want you to write down is transmutation. So transmutation, that's when one atom turns into another atom. For example, you have carbon, you take one of its protons, you turn it into a neutron, it becomes boron. That's an example of transmutation. One element turning into another element. Anytime you have or not anytime. So transmutation occurs in both types of nuclear reactions. However, it doesn't happen all the time. So sometimes you can add an additional neutron, make something less stable, or remove a neutron, make it more stable, and transmutation does not occur. So transmutation can happen. It doesn't happen every single time. Now, the next thing to know about nuclear reactions is that law of conservation of mass is not obeyed. The reason for that is because mass is going to be converted to energy. That doesn't mean that law of conservation doesn't matter here, because law of conservation of mass and energy is conserved. What that means is the mass and energy on one side is equal to the mass and energy on the other side. The mass, however, can change from one side to the other. So if you start with 10 grams of uranium, on the other side you can have 9 grams of uranium, but that 1 gram was converted to energy. So mass can be converted to energy in nuclear reactions. Mass and energy are conserved, however, mass by itself is not conserved. Anytime there's a nuclear reaction, another thing to know is that a large amount of energy is typically produced. Very often, a lot of energy is required to make a reaction take place. However, more energy is produced than is consumed. All right, let's keep going. So we're going to be discussing two types of nuclear reactions. One type is fission. The other type is going to be fusion. Anybody know where the word fission comes from? Good guess. Any other guesses? All right, so if you've ever seen like an enormous boulder with a crack in it, the crack is called a fissure. So the word fission comes from the word fissure, and fissure just means to break in two. So whenever you have fission, this one is fission right here. You have one large atom. In this case, we have uranium-235, and then we shoot a neutron at it. Basically, we shoot it with a bullet, and it becomes very unstable, and then it breaks apart into two different atoms. It becomes barium, and it becomes krypton, and then it also releases a few neutrons. So this is a fission reaction. We're going to talk more about fission in a minute. I just wanted to give you a quick introduction on this page. But whenever we're talking about fission, you always start with one large thing and you turn it into two smaller things, sometimes more than two smaller things. Then we have fusion. Who's seen Dragon Ball Z? What's fusion? All right, the fusion technique, good. So fusion is when you take two smaller things and then you make them one larger thing. So here we have two things fusing into one, and then here we have two things fusing into one, and then here we have two things fusing into one. There's the fusion right there. So fusion is when two things become one thing. Fission is when one thing becomes two things. So the first one we're going to discuss is going to be fission. So what is fission? Fission occurs when a neutron hits a large unstable nucleus, causing it to break into two smaller nuclei. So let's go ahead and write that down. I'll pause for a second and then we'll talk about chain reactions. All right, another thing to know about fission is extra neutrons are going to be emitted, and those cause a chain reaction. So on the previous page, what you saw is just one section of this. So there's our uranium-235. We shoot one neutron at it, and then it breaks apart into krypton and barium. It also releases two neutrons. The neutrons are very important because they're what sustain the chain reaction. So these neutrons, they escape like bullets, and then they hit another uranium-235. Now, what's this one going to do? It's also going to split, and it's going to release how many neutrons? Two. And then here we get two more. So we start with two neutrons, and then in our second generation, we have four neutrons. How many in the third generation? 8 neutrons. And then how many in the fourth? 16. How many in the fifth? And that's a chain reaction. So we start with one, it ends up just increasing and increasing until it reaches an uncontrollable pace. That's what a chain reaction is. So a chain reaction occurs if there are enough atoms present. I'll give you all a second and then we'll move on. All right, so our next term is going to be critical mass. So what is critical mass? Go ahead and write this down. Critical mass is the amount of a substance that must be present for a chain reaction to take place. So I'll give you all a second and then we'll discuss. All right, so let's take a closer look at these images that I got right here. So if you look at, so here's our critical mass. You can see that we start by hitting this uranium with a single neutron. It releases 3 neutrons, and each one of those neutrons hits another uranium, and then releases a bunch of additional neutrons, which hit more uranium. And you can see that a few neutrons escape without hitting anything. However, a majority of them do hit a uranium, which causes the chain reaction to take place. However, if you look at this one, here the first one shoots out 3 neutrons. Each one of them hits something. And then a bunch of the neutrons that they emit end up not hitting anything. So basically, this reaction just fizzles out and stops. So we call this one subcritical mass. Let's come back over here. So subcritical mass, that's when there's not enough uranium or your nuclear material to keep the chain reaction going. For the atomic bomb, 100 pounds of uranium was necessary for a chain reaction to take place. So if you have 50 pounds, what ends up happening? No chain reaction because you have subcritical mass. Anything above 100 pounds would allow the chain reaction to take place. If you have 120 pounds, you get a chain reaction. 150, 200, you get a chain reaction. Anything less, and the chain reaction doesn't take place, and bomb won't even explode. Yeah. Well, each one's got. All right, so can anyone tell me what this is? It is an engine. What else can you tell me about this engine? It is a car engine. It is turbo. That's good. So here we have our turbo. All right, what else? I haven't seen the movie Turbo, but a bunch of students have been recommending it. I'll check it out. But anyway, what else can you tell me about this engine? I'll zoom in if that helps. What can y'all tell me about this engine? All right, so very often students think that cars run on the car battery. So I'm here to discuss with you guys because I want everybody to know how a car actually runs. So so cars, they run on combustion reactions. So how many cylinders is this engine? This is a 4-cylinder. What does that mean? It means it's got 4 combustion chambers. So there's one, there's one, there's one, and then there's one. Now, what do the combustion chambers do? So each one of them, so what do we need to have a combustion reaction? Does anybody remember? when we were talking about types of reactions. You need 3 things in order for a combustion reaction to take place. What are they? Oxygen? Not hydrogen. It could be hydrogen, but in a car, it won't be hydrogen. You don't need to look it up. All right, so fuel is the next one. So you have oxygen, you have fuel. What's the next thing you need? What is it? I heard it. All right, so it's spark. So heat could work, if, but it's going to be excessive heat. With spark, it won't be. You won't need as much heat. So if you have these 3 components, you can make a combustion reaction take place. So inside this engine, you have a fuel rail that's pushing in fuel into each cylinder. It's pushing in fuel at a certain rate. So in our first demo, I want us to ignore the turbo. Let's assume there's no turbo there. This is just a 4-cylinder engine. So it's got you got your combustion chamber. You got the fuel going in. We also said we need air. So this part right here is called the intake manifold, and the intake manifold shoots air into the engine. So you have air and you have fuel, and then you have spark plugs. Anybody ever seen a spark plug? All right, so spark plugs, they take electricity from the battery, and they constantly spark. So they're constantly shooting spark, and you always have spark at about 100%. If it's not 100%, you replace the spark plug and you're back up to 100%. But basically, you're always sparking up, and spark plug is usually a thing you don't have to worry about. Now, in a typical 4-cylinder engine, you could get between 100 to like 120 horsepower. Let's say this engine gives us 120 horsepower. What can we do to get more horsepower out of this same engine? We can't do anything about the spark, but what can we do to get more horsepower out of this engine? We can add fuel. So if we add fuel and we don't add oxygen, what's going to happen? Is all the fuel going to burn? No, because if y'all remember stoichiometry, you got to have the correct amount of fuel and the correct amount of oxygen. It's called your air-fuel ratio. If you increase the fuel without increasing the oxygen, you're running, I forget the word, not lean. You're running rich. So if you increase the fuel without increasing the oxygen, you're running rich. If you increase the oxygen without running the fuel, you're running lean. You got to wait for her to come back. So what do we got to do? We got to increase the fuel and we got to increase the oxygen. How do we increase the oxygen? So can anyone tell me what a turbo does? Say it again. All right, so I'm gonna clear some of this because I want us to take a look at what the turbo is actually doing.
The turbo is blue, right?
Say it again.
Turbo is blue, right?
So the blue is just the air, but so it won't let me draw after I'm zoomed in. So I'm gonna just walk up to the board. All right, so what are some of the drawbacks to having a turbo? So typically, this engine will give you somewhere around. This engine would give you somewhere around 6,000 RPM as your red line. Who's seen the red line on their car? The revometer. It says 1,000, 2,000, 3,000, and then it reaches a point where it just goes red like this. Who's seen that? All right, so most cars, they redline around 6,000 RPM. If you have a turbo, you're redlining at a much higher RPM. Sometimes it's 7,000, sometimes it's 8,000, sometimes it's 9,000. But basically, when you have forced induction, the engine is working harder. If your engine is working harder, just think of yourself. If you drank caffeine all day, every day for the next 5 months, what's going to happen to your heart? Why? Because you're overworking it. So turbo engines, that's one of the big downsides to turbos. You are overworking the engine. However, there's a lot of benefits to having a turbo. So you can get V8 power out of a 4-cylinder, which is much more lightweight than a V8, much cheaper to manufacture than a V8. That's why manufacturers love these turbos. They produce more power and they're more compact, they're more lightweight, and they're much cheaper to manufacture than they are to just install a V8.
They're convenient, right?
They do consume more fuel, but they can be more efficient than, like, it's more efficient to get a turbo 4-cylinder than a V8. It's more efficient. Now, 18 wheelers, they all run turbos. I'm pretty sure your buses that bring you to school, they also run turbos, because it doesn't make sense to increase the size of the engine. You can make an engine work harder just by forcing more air into it. Now let's take a look at the next slide. Can anyone tell me what a supercharger is? All right, so how is a supercharger different from a turbo? What does that mean? All right, it's not using the air. Good. So it does the same thing, except it runs off a completely different mechanism. We were talking about how the exhaust is constantly putting out pressure that's unutilized. This uses a completely different mechanism. So here's your crankshaft, and your crankshaft has belts coming off of it. And these belts, they go to your power steering, they go to your alternator, they go to your brake booster, they go to all different places. And what a supercharger does is it just attaches an additional belt to your crankshaft, which means this rotation that your engine's doing at idle, the supercharger just takes that and then turns that rotation into suction from the intake that ends up going to your intake manifold. And it just utilizes a different power source to do the exact same thing. Has anyone ever heard of twin charged? What do you think twin charged means? Bless you. What do you think twin charged means?
Twin charge?
Yeah.
Charge at the same time on the same thing.
All right, so it's got a turbo and it's got a supercharger. So that's going to be twin charged. Now, why are we talking about turbos? Some of y'all may be wondering. They're not nuclear. So the inventor of the turbine, the electrical turbine, was actually Nikola Tesla, and I have one right here. So this part right here, it looks like a motor, was invented by Tesla, and it's one of the most valuable inventions of the 20th century. These things are everywhere. They're in electric cars. They're also in your phones. You know when your phone vibrates, how does your phone vibrate? What does it do? But how does it do that?
I guess it's because of that thing.
All right, so it's got one of these motors, and it's got a weight on it, and it applies power to the motor. The motor spins, and that's the vibration that you feel in your phone. So these little motors are everywhere. They're also in your blow dryer. So your blow dryer runs off a motor just like this. So you increase the power, it spins faster. Your fan, this air filter, Tesla cars, these motors are everywhere. So it's a very valuable invention. Now, what's the most valuable part of this invention? So if we apply an electrical current to this motor, it spins, okay? What do you think happens if we spin the motor? What does it do if we spin it? All right, so if we apply energy, it rotates, and if we rotate, it gives us energy. So that's the important thing about this turbine. That's why we were talking about turbos. I wanted to show you all this turbine. Now, I want to talk about this traditional coal-fired power plant. So about 50% of the energy in the United States comes from power plants just like this one. So I want everybody to take a close look. I'm about to discuss it real quick. If you did your project on a nuclear reactor, you probably saw an image very similar to this one. So we're going to start by discussing this one, then we'll talk about nuclear sites. So in a coal power plant, you have coal, you have a thing that pulverizes the coal, and then it goes into a boiler, which is just a spot for the coal to burn. Now, up here, we have the exit point for the smoke. So a bunch of energy is actually lost in the smoke that's escaping. And then here we have cold water. Bless you. We have cold water that's running through this pipe, and then this pipe goes into the boiler as a coil. What do you think happens to the cold water as it enters the boiler? All right, so it increases in temperature and then it vaporizes. And what does liquid do after it vaporizes? What happens to its pressure? What happens to pressure when you convert water to steam? All right, pressure goes up. What happens to volume? Does it go down? When you go from liquid to gas, what happens to the volume? It expands. So here you have water turning into vapor, and this hot vapor runs through this turbine, and then what does it make the turbine do? It spins the turbine, and then the gas turns back into a liquid, and then does the cycle over again. And as you turn this turbine, what happens? What do you produce? You produce electricity. This is how all the electricity in the world is made. You always have water that turns a turbine, and you always have a boiler that's heating up some type of material. And natural gas power plant runs the exact same way. The only difference is instead of having a coal-fired boiler, you're going to have what looks like your stovetop and just natural gas burning and heating up these coils. Any questions on our coal-powered power plant? All right, let's keep going. So here we have nuclear fission. So this is what a fission power plant looks like. About 20% of our energy comes from fission. So 1 out of every 5 of you, your entire home is powered by nuclear energy. So nuclear fission releases a large amount of energy. So let's go ahead and write this down. If you know that it releases a large amount of energy, you don't need to write that. What you do need to write is that it's exothermic. What does that mean? It releases energy to its surroundings. Bless you. In nuclear power plants, the energy and chain reaction is controlled and slow. So we can speed up and slow down these chain reactions. In the atomic bomb, the fission reaction is uncontrolled and very fast. So let's take a closer look at this reactor. All right, so in nuclear reactors, the heat generated by the reactor is used to produce steam, which turns a turbine that generates electricity. Here's just another picture of what you guys just saw. Again, here you can see the control rods. And then here you can see the dome, the containment dome, which is typically about 3 feet of concrete to keep the radiation in. Okay, so real quick, I want everybody to draw this and label it. So on your quiz, there's a very good chance that you guys are going to have to not draw this thing, but you're going to have to label this thing. So I'll give you all a few minutes to go ahead and draw this in your journal. All right, so let's discuss these components real quick. All right, so number 1, that's going to be your containment dome, and that's typically going to be concrete, 3 feet of concrete. Here you have your reactor. So number 3, this is our reactor. And this is going to be our control rods. They speed up or slow down the reaction. Number 5, that's going to be our steam. And of course, down here, number 4, that's going to be our steam generator. That's just going to be the water. And when it gets hit by the hot water from the reactor, it vaporizes and turns into that steam. Number 6, this is your electric generator. And number 7, this is called your condenser. This part is really important. This turns this steam back into water so that it can be reused by the reaction. Over here, all of these are pumps. Pumps are crucial to keep everything moving. If anything stops, if any of the pumps stop working, you get an overheat, you get expansion, which causes pipes to burst, and you definitely don't want that. Any questions on this? All right, let's move on. Okay, so nuclear accidents. I'm not going to talk about these because you guys did projects on these. But one thing to just know is typically our issues are related to coolant. So they're always coolant systems that cause issues at nuclear power plants. All right, next up we have nuclear fusion. We're almost finished. We're just going to discuss fusion real quick and then we'll be done. All right, so what is fusion? Go ahead and write this down. Small nuclei fuse together to form a heavier nucleus. So currently, successful fusion is happening in the sun. Who's seen this movie? Who's seen this movie? Do what? That's Spider-Man 2. Are y'all kidding? He goes, the power of the sun in the palm of my hands. And then the reactor does what? It explodes, and then you get a magnetic force and all that stuff. But basically, up till this point, we haven't. Well, actually, we have. We'll talk about it in a second. So fusion occurs in the sun. That's where successful fusion takes place. It's responsible for the light and energy given off. Again, it's exothermic. And the primary reaction is going to be hydrogen atoms combining to form helium atoms. So 2 protons bonding with each other, forming helium. So when I was in school, they told us that fusion only takes place in the sun. But now we can tell you that we do have fusion reactors here on Earth. There are some in France, there are some in California, There are some in Japan. There are some in China. And everyone right now is trying to get fusion reactors to work. The problem is they consume more energy than they produce. So it takes 20, let's say, megawatts of energy to get this reaction started. And then we can only take out 1 megawatt of energy after it starts. We can keep it running for, let's say, a minute, maybe 2 minutes. And China, they were very successful recently. They got it to run for 200 seconds. But that's as long as we've been able to keep it running and removing energy from it. Once we can start it up with 1 megawatt and get 20 megawatts out of it, that's when nuclear fusion would be a viable energy source on Earth. Yes, sir. Yeah, but not much. Like we need it to be like 2-fold, 3-fold. Then it makes sense because they're really expensive to build. You gotta be able to afford to build them. Anyway, let's keep going. So nuclear fusion is the products of nuclear fusion are not radioactive. That's the big thing regarding nuclear fusion. It produces helium, and helium is, as y'all know, noble and non-reactive, so it's an excellent byproduct of an energy source. Like it wouldn't contaminate the same way any of the coal does, or the natural gas, or fission, because fission leaves radioactive waste. With fusion, you don't get radioactive waste, which makes it an appealing energy source. The problem with it, though, as you all know, these protons, they don't repel or attract each other, so getting them really close together and getting them to fuse requires a lot of energy, which is why we don't currently have nuclear fusion. This is called the Tokamak Fusion Reactor. This one's at Princeton University. This one was one of the first we had in the US. This is what the inside of it looks like. But this has been able to make fusion take place. Here we have isotopes of hydrogen that you need for fusion. So we have deuterium and tritium. You fuse those together and you get this helium. You don't need to know these, though. These are not tested. I just wanted to show them to you. Any questions on nuclear fusion? All right, let's move on. So let's compare and contrast real quick. You already wrote all of this stuff, but let's recap, because this you'll be tested on. You'll see 2 questions on the ACP regarding this slide. What do these 2 have in common? So with both of these, there's a change in the nucleus. That's one thing they have in common. They both create large amounts of energy, enormous amounts of energy. Transmutation can take place in both of them. So both times you get transmutation, elements change from one element to another. So a change in the number of protons. Now, how are they different? With fusion, you're taking 2 small atoms, making them larger. Or you're taking 2 small atoms and you turn them into 1 large atom. Another thing you need to know about fusion, there is no radioactive waste. Any one of these could be a question. And next thing is fusion is very, very hot. Like compared to fission, much, much hotter, 5,000 degrees Celsius. Now here with fission, you're going to take a large atom, split it into smaller atoms. You're also going to produce radioactive waste, which takes a long time to decay. And this is very likely what your test question is going to look like. Which of these are used in nuclear power plants? You need to know that that's fission. So currently, all power plants are fission reactors. Any questions on this? All right. And we're almost finished. We're just going to talk about isotopes real quick. But before we talk about isotopes, let's get some definitions. Y'all remember these from the beginning of the year. Looking at my periodic table, which of these numbers is your atomic number, blue or red? Which one's the atomic number, blue or red? Blue. It's the smaller number. The smaller number is going to be your atomic number. And what does it tell you? It tells you your number of protons. It also determines the identity of the element. If you forgot that, write it down. But that's something you got to know. Now, what is the mass number? Mass number is just going to be your protons plus your neutrons. So if you know your identity, if you know which element you're looking at, and you know the mass of the element, then you could determine your protons and neutrons just off those two pieces of information. Now, our next definition, I suggest you write this down because a bunch of y'all did forget this one. An isotope is going to be atoms of the same element that have different number of neutrons. We'll talk about them on the next slide, but I want you to get the definition. So they have a different mass number, but they have the same atomic number because they're the same element. For example, carbon 6, carbon 12, carbon 13, carbon 14. Okay, let's move on. So here we have three isotopes of carbon, carbon 12, carbon 13, carbon 14. And these things we discussed at the beginning of the year, but we just got to go over them again. So what does the 12 tell us? What does the 12 tell us? Is that the number of protons? What is the 12? It was on the last page. What? All right, so it's the mass number. And the mass number, as we know, is protons plus neutrons. Now carbon, what does carbon tell us? It tells us the number of what? If we know that we're looking at carbon, what do we know the number of for sure? Protons, because all carbon has how many? All carbon has 6 protons. So if I say you have carbon 12, can you tell me how many neutrons you have? You have 6, because 12 minus 6 is going to be 6. What about carbon 13? How many neutrons? Carbon 14. So it's it's valuable information. You have to know what element you're looking at, and you have to know the mass number. So the mass number is the thing that's always going to be included. You just got to keep that in mind. Now, this is called nuclear notation. We talked about this at the beginning of the year, but we're bringing it back. This is very important. So nuclear notation, you're going to be seeing a lot of this now. What is the smaller number? It's the same thing. What is the smaller number always? That's your atomic number. That's going to be your number of protons. What's 235? Protons and neutrons. So that's your mass number. So to figure out our number of neutrons, what do we have to do? 235 minus 92, that tells us how many neutrons we have. So all three pieces of information here are valuable. We need all three when we're writing in nuclear notation. So go ahead and write uranium. I want you to have that just so you know what nuclear notation looks like, and label it as nuclear notation. Next time y'all come in here, we're going to be working with nuclear notation. Another thing you're going to see in nuclear chemistry is going to be hyphen notation. So hyphen notation, it just tells you what element you're dealing with, and then it also gives you the mass. So uranium-235, that's uranium, and uranium has how many protons? It's got 92 protons. If it's got a mass of 235, can you figure out how many neutrons? Yes. So uranium-235, that's all the information you need. What about U-235? Is that all the information you need? Yes, because U is what? U is what? Uranium. So these are both hyphen notation, and then up here we have our nuclear notation, and you'll need to be able to work with that. Any questions on nuclear notation? All right, next class we're going to talk about decay, and that's going to be it for today. So go ahead, work on your projects from now till the end of class.